All right, number 5. So this is the same idea, except now we're going to incorporate a second derivative. So I've got this equation, g of x equals 1/3 x cubed minus x squared minus 3x plus 4. Take the derivative. That would be x squared minus 2x minus 3. Now I'll take the derivative again. That would be 2x minus 2. Okay, let me double check this because I wouldn't want to get it wrong. Okay, bring down the 3. Cancel x squared minus 2x minus 3. Okay, that looks good. So now I'm going to use this to fill in my table again. Luckily, this will be a little bit easier. Well, it's easier and harder, so I wish I hadn't said that. I'm going to start with this one, this column, because it actually is quite easy. It's 2x minus 2, and I can already kind of see the pattern. You're subtracting, it's by 2's, so negative 10, negative 8, negative 6. So I think it's actually adding 2. It's just weird because it's negative. And then I'll check 0. That makes, let's see, at 1, that does make sense. Okay, and then I'll check again to make sure 10, just to make sure I got my pattern right. 2 times 10 is 20 minus 2 is 18. So just like to reiterate, this 10 is telling me that if I plug in 10 into my derivative, I get 18 out. So I know that has something to do with concavity. We'll talk about it more in a second. Actually, let's do it now. So if you take the second derivative and you plug something in and you get something negative, that means it's concave down. So all these values are concave down until, whoops, I got a little overexcited. Concave down until here. And then here it's unknown. We have to test some points. Just put a question mark. And then it's concave up from here down. So yeah, if you remember this right here, when the second derivative is 0, tells you it's a possible inflection point. So we'll have to come back to that to fill that in. And then for the rest of this table, I'm going to use a calculator because it's a quadratic. So give me a second to get myself ready. Okay, so we have, let's see, the first value I need to do is negative 2. So I would do negative 2 squared minus 2x, or negative 2 minus 3. Okay, so I get 5. Okay, now I'll plug in negative 1. I get 0. Plug in regular 1. Get negative 4. Okay, so this is looking exactly the way I would think a quadratic would look. And I bet this is a pattern now. You can kind of see like there's negative 3, negative 4, negative 3, 0. So I bet this is 5, 12. Okay, now I have to plug in 8 though if I'm going to keep going with this pattern. Okay, I've got 45, and then the last one I need to do is plug in 10. 77. Okay, now let's see. Find the missing values in the table. Okay, so actually what I should check is whether it wants me to graph the derivative or the second derivative. Oh, it sounds like I should be doing, oops, remnants from when I practiced. I don't practice, no. This means that they graph the derivative. So yeah, I think we're supposed to graph the derivative. Okay, so we have the original function here. Sorry about the music coming from my son's show. There's no babysitters in the coronavirus except for TV. Okay, now I'm graphing the derivative. This one is a little bit more complicated because it's not a straight line. So I'm gonna plot points a little bit more than I had before. -3, 12, -2, 5, -1, 0, 1, -4, 2, -3. Uh-oh, let's see. I think I messed something up. I got distracted. Okay, so at -1 it was 0. I drew that kind of wonky. And then at 0 it was -3. At 1 it's -4. Okay, yeah, no, I was fine. I just panicked. 2, -3. And 3, 0. 4, 5. Okay, so I'm getting pretty good U shape happening. Okay, and then let's see, 5 is 12. Okay, I think that's probably good. Okay, so I've got an original and I've got a derivative. Okay, g of x is concave up over the interval. Okay, so let's do that thing where we kind of ignore everything and we'll just sort of talk about the two things that I'm seeing here. So just looking at the graph, ignoring everything else. So I'm supposed to think about concavity, and I can see in the original that it kind of switches at 1. So it's concave down, and then it's concave up. So let's see how close I was, because we actually know from the table where that switches. So it's concave down until 1. Okay, that's awesome. And then it goes back up. So actually, according to this is an inflection point. So I think we can put that in. Inflection point. Because it changes its concavity. So that's cool. So it's an inflection point. Let's see. So we talked about that. One thing to think about is how are we seeing that on the derivative? So notice that on the derivative at 1, so this is an inflection point, down here is a minimum. And so this is a weird thing to think about, but the slope of the derivative tells you about the second derivative, which is 0. The slope of the derivative is 0, which tells me that the second derivative is 0, and that's actually something we already knew. We knew the second derivative was 0 at 1. So that's cool the way that's matching up. Let's see, what else can we think about? So we've done concavity. Let's think about our mins and maxes. So at -1, around there somewhere is a maximum. And actually that works out perfectly because we already know if there's a maximum on an original, the derivative should have an x-intercept that should go from positive, which it seems to be doing, to negative. That's pretty handy. And then let's see, what else do we have? We also have a minimum at 3. Oops. We have a minimum at 3 that shows up as an x-intercept on the derivative. And at that x-intercept, it goes from negative to positive. That's pretty cool the way things are kind of showing up the way we would expect. So let's see what we can write about that. Okay. G of x is concave up over the interval from -∞. Oh wait, that's not true. Concave up from 1 to infinity. We can see this in the graph and in the table because the value of the second derivative is 0. Actually, that's not a great way to put that. We can see that because the value of the second derivative is positive. Right? So just to talk this over one more time. So for the original, 1 to infinity is where it's concave up. That's all of this stuff. In the table, 1 to infinity is where these values are positive. And then the inflection point, which happens at 1, is 0. So it's 0 and up. That interval, that open interval, is going to be concave up. This means that the graph of the derivative is increasing. So this is a weird one, but we did talk about this, increasing over the interval 1 to infinity. So when we look at the derivative from 1 to infinity, notice that the slopes are increasing. So that's like saying the second derivative is positive. If the slope of the derivative is positive, then the second derivative is positive. Pretty nice. Okay, g of x is concave down over the other interval, so negative infinity to 1. We can see this in the graph and in the table because the value of the second derivative is negative. This means that the graph of the derivative is decreasing over the same interval. Okay, let's check this one more time. Okay, so we are looking at the original. The original is concave up from negative infinity all the way to 1. You can see this in the derivative because its derivative has negative slopes until 1, which means that the second derivative is negative. You can see this in the table because from negative infinity all the way to 1, these values are negative. Well, hopefully that helps a little bit. Let's stop there and go on to the next one.